Now, some regions are best treated by regarding x as a function of y. Now, if a region is bounded by curves with the equation x is equal to f of y and x is equal to g of y, and y is equal to c and y is equal to d, where again f and g are continuous functions, then we would say that the curve on the right side is greater than the curve on the left side. And so figure 9 is now showing this. So we have a horizontal line at y equals c, therefore that's the lower bound, or the lower limit, excuse me, and then the upper limit would be y is equal to d, and you have these two curves. Now we write x is subscript r for the right boundary, and we write x subscript l for the left boundary, and therefore we would have the formula where a is equal to the lower limit of c and d x subscript r minus x subscript l dy, since we're taking the antiderivative with respect to y. Now let's integrate with respect to y is sometimes easier. We want to find the area enclosed by the line y equals x minus 1 and the parabola y squared is equal to 2x plus 6. Okay, now once we, in order for us to first figure out what this graph looks like, on your graphing calculator, because it's only interpreted in terms of y, then you need to put the function in terms of y, which is y is equal to x minus 1. And you would find the square root of both sides, and therefore y would equal positive square root of 2x plus 6 and minus the square root of 2x plus 6. And therefore that would give you these curves. Now, what we want to do is we want to solve these two equations. Now, here in this first part, we have y is equal to x minus 1. Now, since we know that this is y squared equals 2x plus 6, instead of taking the square root of both sides, what we could possibly do is square both sides for y. Now, it doesn't matter which way you go. What I decided to do was square both sides. So now we know that y squared is going to equal x squared minus 2x plus 1. And then we know the other function y squared is equal to 2x plus 6. And therefore, we can set those two equations equal to each other. Now, once we set them equal to each other, then we would get a trinomial, and we can factor. So we know that the x is going to equal negative 1, and x is going to equal 5. But what we're looking for are the y values. We want to know what the lower limit is and the upper limit is. So if we plug in negative 1, then we would get negative 2 as the output. So therefore, the lower limit is going to be negative 2. If we plug in 5 into the function, we get y is equal to 4. So therefore, y is equal to 4 is now going to be the upper limit. Now, the next step is now we want to be able to convert this in terms as y, x is a function of y. So we're going to solve for xr. Now, since xr is the line to the right here, y is equal to x subscript r minus 1. Add 1 to both sides, therefore xr is equal to y plus 1. And then for 2, we're going to solve for xl. So therefore, y squared is equal to 2xl plus 6, solving for xl, which results in 1/2 y squared minus 3. So now we know what our functions look like, and we also know what our upper and lower limits are in terms of y. So here we have our area that goes from a lower limit of negative 2 to 4, x to the right minus x to the left dy. So we have y plus 1 minus 1/2 y squared minus 3. Now we can distribute and combine like terms, and therefore now let's take the antiderivative of each term, going from a lower limit of negative 2 to 4. If we plug in those values, then we would get the result of an approximating area, or in this case, the area would equal 18. Now, we could have found the area in example 5 by integrating with respect to x instead of y, but that calculation is much more involved. What it would mean is that you would have to split the region in two and then compute the areas labeled A1 and A2 in this figure. The method that we used at the beginning was much easier. So in this case here, you're going to have one area that you need to find and another area.